All right, this is Monday, January 4th, 2021, Aerospace Engineering, a debrief on the assessment that was taken just before winter break, where one of the challenges was for students to work out the reaction forces for a given truss structure. This particular problem looks very intimidating, and that was by design. There are some students who even made an attempt to work out what the reaction forces, what the tension and compression forces were for each member of this truss structure. But that's not what the objective was on this problem. The objective was determine the reaction forces acting on this thing externally. So here's this complicated structure. I'm pushing down on it at this point with 150 newtons, we'll call it. I'm pushing to the right at this point with a force of 350 newtons. And the question becomes, so what pushes and pulls do I need here at what we'll call point A, or over here, we'll call this point B, such that the sum of all the forces horizontally add up to zero, the sum of all the forces vertically add up to zero, and the sum of all the moments or twisting torques about any arbitrary axis of rotation also add up to zero. Now I'm going to choose to put my axis of rotation on the left corner at point A, but that is an arbitrary choice. You can put the axis of rotation anywhere that's convenient for you. Here we go. This 150 Newton force is pushing the structure downward. So there must be 150 newtons upward force going on between point A and point B. But I'm not going to start by doing that. I'm going to start by analyzing the moments, the torques, the twisting forces that are trying to rotate this thing. So I'm interested in this 150 newtons is pushing down at a distance of 3 meters along its line of action from the axis of rotation. So let me say that again, kind of. I chose my axis of rotation to be at point A. This 150 newtons is really, by Pythagorean's theorem, it's 3 squared plus 3 squared is 3 times the square root of 2 meters away from point A. You can do it that way. You could say R is 3 times the square root of 2 meters. The direction from R to F is taken to be 0 degrees. On this printout, it says, oh, look, here's an angle of 36.870 degrees above the horizontal. That is not the angle that we would use for theta. We would say, I'm going to take the direction the pen is pointing, that's R, and I'm going to call it 0 degrees. The direction that F is pointing is vertically down. What is the angle between the direction of the pen and the direction of my finger? Well, first I rotate it 36.870 degrees, and then I rotate it an additional 90 degrees, and I get my answer. Oh, this angle is 126.870 degrees. And that's what I would have to type into my calculator, right? Let's see, 3 plus 9 is 12. 126.870 degrees. And in the negative direction, if I use R is equal to 3 times the square root of 2 meters by Pythagorean's theorem, and I use negative 126.870 degrees, I will get the moment caused by this 150 Newton force applied at this distance at that angle. The trick I've been sharing with you students is that I will get the same answer if I slide this force along its line of action. That means I can move it in the direction the arrow is pointing, and it won't make any difference in the answer. I can move it backwards from the direction the arrow is pointing, and it won't make any difference in the answer. As I move it backwards, r becomes greater. The angle also changes, and their product, the sine of this angle and r, will work out to the same product. What I'm going to choose to do is to slide the force forward until the direction from r to f becomes a convenient negative 90 degrees. That means F is right here. Instead of being up here at 3 radical 2 meters away from A, the distance has decreased to where it's just 3 meters away from A. The angle is negative 90 degrees. Sine of negative 90 degrees is negative 1. So this moment becomes negative 3 times 150 Newton meters. Newton meters. That is the moment caused by this one force. There is a second force also trying to rotate this thing clockwise. Now, if this arrow were pointing to the left instead of pointing to the right, then you have a more interesting problem where this force is trying to make it rotate clockwise, while that force is still trying to make it rotate counterclockwise. Okay, look at that visual, great. All right, I'm pushing down, it's trying to rotate it clockwise. This one, as written, is also making it rotate clockwise. Okay, so it's making it rotate clockwise. Great. Well, I'm going to slide it along its line of action. Make my life easier. Because I can't just add this distance to that distance. By the way, I see I used the wrong angle here, and not one of you students corrected me on it. For this situation, I should have used 135 degree angle as the angle between R and F. Okay, why is that? Because it changes direction here a little bit. It starts off at a 45 degree angle, and that's the one I should have been using. Later on, the angle decreased to 36.870 degrees, but I don't care. So back here, this was incorrect. The value I should have used was negative 135 degrees. And my claim is the sine of negative 135 degrees times 3 times the square root of 2 is, believe it or not, equal to 3 times the sine of negative 90 degrees. You can check that on your calculator. All right. Anyways, if I wanted to get the value of R from A to this point up here, I should use the graph paper and say, look, this is 1, 2, 3, 4, 5, 6, 7 units to the right, 1, 2, 3, 4, 5, 6 meters up. Use Pythagorean's theorem for this right triangle. Don't use this angle because it's wrong. Don't use that angle because it's wrong. If you do it, it'll work out. I'm going to use my trick of sliding the force along the line of action. In this case, I'm going to back it up. I'm going to move that 350 newtons until it is directly above point A. So here it is. I've slid this force until it is perpendicular to R. Here's my new R. It is 5 meters. My force is 350 newtons. The angle is negative 90 degrees. The sine of negative 90 degrees is negative 1. So this becomes negative 5 meters times 350 newtons. These two moments are both rotating this complicated truss clockwise. The only way I can stop it from rotating clockwise is at point B, I have to push up with the correct amount of force to cancel these moments. Okay? I don't care about the forces. I care about the moments, which is the product of R and F. B is located 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 meters to the right. The angle from R to F is going to be positive 90 degrees. So that makes it, of course, a plus sign. Sine of 90 degrees is 1. Times the reaction force at B in the vertical direction. These two negative moments added to this one positive moment have to all add up to 0. So this is where I would pull out a calculator and I would say, what is, well, I guess you could do the first one in your head. What is 3 times 150? And I get negative 450. What is 5 times 350? And no, I already can't do that one mentally anymore. It's 1750. And why is my phone? Oh, okay. So I have a total of negative 2200 Newton meters. Divide that by 10, and I get the reaction force at B is 220 newtons. Let's go to the answer key because I'm, worried about that. I have a wrong answer. Kids, where'd I go wrong? Wow, science department has got a lot to say. Let me silence my phone. Kids, where'd I go wrong? Did I type the wrong number into my calculator? I did not, right? I have 3 times 150 is 450. And 1, 2, 3, 4, 5, 6, 7. Oh, here's my mistake. No, that's not my mistake. I'm sorry. 5 times 350 is 1750. Add the two together, I get 2200. Oh, let's see. Is someone going to help me? Was that a comment from somebody that I missed? And the answer is someone made a comment. Isn't it 6 instead of 5? Maybe. Sure is. That's 5. That's 6. There's my mistake. Oh well. Aren't you glad I didn't design the bridge that your mother has to drive over to get to any place these days? So the correction is this is negative 6 times 350. And yes, that makes it match the answer key now. So let's see. 6 times 350 is 2,100. Add to that 4,000, or add to that 450. You get 2,550, which you can't quite see. Divide that by 10, and you get 255 newtons. Thank you, Savina. I should give you extra credit. Yeah, sure should. Okay, there. I finally have one piece done correctly. There are no horizontal forces at B because it's a roller. It would roll if you applied a force. So everything else now has to be figured out at point A. There must be 350 newtons to the left at point A, because that's the only way to cancel the 350 Newton load to the right. Now, vertically, here's where some of you made mistakes. Not that I didn't make one myself just now, but vertically, 255 newtons pushing up at B added to 150 newtons pushing down at A. And what's going on at A vertically, when added to these other two vertical forces, they have to all add up to 0. So I could say, how would I say this? I could say 150 newtons pushing up minus 255 newtons pushing down means crazy enough, but I have to be pulling down at A, not pushing up, with a magnitude of 105 newtons. Most of you who made a mistake on this problem had this reaction force going up instead of going down. Oh well, so I had to take points off. I believe I now have the correct answer key. Yeah, okay, I finally got this one right. Again, we don't care how complex this structure is on the inside. All we care about was the analysis of what are the reaction forces on the outside at point A and at point B. It was the last problem where, look, see, I tried to make it kind of simple. And I said, okay, this time, go and do everything. And as you can see, this period, it looks like the only thing I'm doing is debriefing you on this exam. I'm going to create homework due Wednesday, and part of it will be updating me on your status for different software. Here we go. At kind of ludicrous speed. I have two reaction forces going on, or two loads. I'm sorry, these are called loads going on. For one of them, 350 newtons, it's 1 meter from the axis of rotation after I slide it, and it's clockwise. So minus 350 Newton meters. The 50 Newton load is 7. I'm learning to pay attention. Thank you, Silvina. 7 meters away. So 7 times 50 is 350. It is also negative. So these two moments add up to negative 700 Newton meters. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 meters to the right, the reaction force at B has to be pushing up with positive 700 Newton meters. 700 divided by 10 means 70 newtons pushing upward at point B. And of course, I'm going to try to look up the answer key, see if I got it right. Oh my goodness, I did. So far. At A, I have to be pulling to the left with 50 newtons. The sum of all the forces vertically have to add up to 0. So I have to push up with 350 newtons and pull down with 70 newtons. So if I go 350 minus 70, I get 280 newtons pushing up. Now, by the way, this must be done correctly first. It is impossible to get correct tensions or compressions for the interior members if the external reaction forces are not first done correctly. And so that was my strategy on this test. I gave you several problems to get the reaction forces. And now this last problem that says, great, do the reaction forces, and now let's go inside. I like to start over here at B. It just is easier for me mentally to figure out what's going on. Mentally, I see I'm pushing up with 70 newtons at point B. Member AB can only pull or push horizontally. Motion in one direction is independent of motion in a perpendicular direction. So the only way I can keep this roller from actually going up under the 70 Newton vertical applied force of the ground is if member BC, I'll call this point C up here, and point B down here, and point A over there, is member BC must be pushing down with a vertical component of 70 newtons, canceling the ground pushing up with 70 newtons. Well, the side effect of BC pushing down with a vertical component of 70 newtons is that it's also pushing it to the right by some force. The geometry is, these are similar triangles. So this triangle is 7 meters high, 9 meters wide. This right triangle here for member BC. So for every 70 newtons that it pushes down vertically, it's pushing to the right by 90 newtons. So it's pushing 70 newtons down and 90 newtons to the right, matching the geometry that says, oh, it's 7 meters up, 9 meters to the side. Great. I can use Pythagorean's theorem to calculate the resultant hypotenuse. 70 squared plus 90 squared will be the force on this of member BC. And since it's pushing to the right, it is under compression. It is pushing apart. It's shoving. So square root of 70 squared plus 90 squared is 114.0175425. Call it 114 newtons. Member AB, next one. Okay, I'm moving on. This one is easy. If BC is pushing B to the right by 90 newtons, then member AB must be pulling B to the left, so it's under tension, by 90 newtons. Ta-da! For point A or for point C, you pick which one you want to do next. Oh gosh, I haven't picked on anyone all period. I've not heard one meaningful word out of any student. What if I just call on someone? Oh wow, Louisa. Should I try to analyze point A or point C next? Random choice. Okay, I'm going to work on point C. If BC is pushing B 70 newtons down and at the same time 90 newtons to the right, that means the other end of it is pushing 70 newtons up and 90 newtons to the left. It's the opposite side of the same stick. So 70 newtons down and to the right on the B end is 70 newtons up and 90 newtons left on the C end of member BC. All the forces here have to add up to 0. What have we got? We have 70 newtons to the left and 50 newtons to the right. They do not cancel. So member AC must be pushing 20 newtons to the right to cancel the difference between 70 to the left and 50 to the right. Vertically, the load is pushing down on point C with 350 newtons, but member BC is pushing upward with 70 newtons vertically. Between these two upward and downward forces, that works out to be 280 newtons pushing down on point C. To cancel that, member AC must be pushing up with a force of 280 newtons. Now I can figure out what is member AC doing. It is under compression because it's pushing apart A from C and C from A. It's pushing these two apart. So it's under compression. Tension, oh man, here's the end of the period. Tension is when they pull together. All right, let me finish this off. I use my calculator to find the resultant of 280 and 20. The square root of 280 squared plus 20 squared is 280.7. I'll call it 281. I'm just going to round it off. And technically speaking, this completes our analysis. I'm not sure if I need to bother doing A. I am going to dig up the answer key. And I see I have a rounding error. Here was the answer key. They call it 282 here. Maybe I typed the wrong number into my calculator. Who knows? Okay, I am going to go see if there's any CHTV. All the messages from the science department while we were talking imply that there is no CHTV today, but I don't know. So I'm going to go look it up right now. I also realize I'm still recording. So let me shut off the recording.